Okay, we'll do the slideshow from current slide. And before we get into equations of the quadratic type, let's go back to example 2. We did example 1, which is on the board here, or the last part of it. But let's pick up with example 2, because they don't have that in the PowerPoint. And we may even turn on the projector just for time. Okay. Well, actually, that was for Amber.
Huh? Yes, I realize this. Also, what did last Thursday?
Do you watch NBA basketball?
Not much. Why?
Do you know who James Harden is?
Who?
James Harden.
James Harden?
Plays for the Houston Rockets, number 13.
Uh-uh.
Never mind.
Why? What did he do?
No, he's like, you know how like some players have their trademark?
Right.
Okay, well, he has a huge beard, and he shaved it. He looks really funny without it, so I didn't know if you knew who he was.
Oh, I see. I may have seen him. Do you have a picture?
Yeah, that's him.
Oh, that's before and after.
Yeah,
Oh my goodness, he looks so young.
yeah, it looks weird.
Yeah. You sure that wasn't his high school picture? No, that's all right. Okay. We are in chapter 5, solving trigonometric equations. Chapter 5 is analytic trigonometry. 5.3 is solving trigonometric equations. And we had done example 1 last time. This was the last part of it here, but we're starting on example 2 today. Page 365. Okay. All right. This one is 3 times the tangent squared x minus 1 is equal to 0. There's a trigonometric equation to solve. How do you go about solving it?
Yeah, put it in terms of sine and cosine.
Not really. Okay.
That
That was when we were verifying trigonometric identities. That's a good thing to do. Not always, but it's always a good thing that you can try when nothing else works. This is solving an equation. We're trying to find the value for x, which makes that equation true. Now, if that was an equation in y, say, 3y squared minus 1 is equal to 0, what would we do? Absolutely. Okay, add 1 to both sides. What we're doing is solving first for the tangent, then we'll try to solve for the x. That's the steps now. Solve for the trig function first, then solve for the x, so for the variable. So we'll add 1 to both sides, and that gives us 3 tangent squared x is equal to 1. Now what? Divide by 3. Sounds like a capital idea, okay? The 3's go out, and now you have tangent squared x is equal to 1/3. And now what do we do? Take a square root of both sides. That would give us tangent x is equal to plus or minus the square root of 1/3. But you can clean that up just a little bit because you know the square root of the numerator, 1. So that could be plus or minus 1 over the square root of 3. Now, are there any angles x whose tangents look like either plus the square root of 1 over 3 or minus 1 over the square root of 3, or whatever I said? Second? Okay. If this were a tangent, which it is, then this x would be an angle. Let's do it in the first quadrant. Okay? In the first quadrant, if that is your angle, pretty ugly, but if this is the angle x, tangent is 1 is opposite over adjacent. Right? Okay? This is using the positive now. What would the hypotenuse have to be? Okay, and what did you say it would be? Okay, you may. I'm not going to. You can. That was the royal you. Okay. All right. Chevette is here. 2. Very good. Okay. Now, does that look like any of the angles, and mine isn't drawn anywhere close to scale? Do we know anything about that? In fact, if I were to draw that to scale, this would be something more like this, this, and that. Root 3, 1, 2. This is the angle x. Is that any of our favorite angles? Huh? Definitely. Come on. Short side is half of the hypotenuse. What angle is that true for? 30 degrees, or pi 6, right? So that could be, so x could equal pi 6. Now they didn't put any restrictions on us here. So then, but with tangent, what is the period for tangent? Say again? Just because we did it last chapter doesn't mean we have to forget about it. What's the period for tangent? 4 of our trig functions have period of 2 pi. And tangent has period of pi, exactly. Okay? So that would be pi 6 plus n pi. And what's the other possibility? The one with the minus sign, that would have been down here, right? Same deal, huh? And that would have been minus pi 6 plus n pi. Okay, those are the 2 possibilities for this one. Now, if you don't like using the minus, the other possibility would have been go all the way around to here. And that would have also been here. And that would have been 7. Wait a minute. Oh, no, I'm sorry. That would have been the same as the one we just did. Not that far. Okay. The other one that has a negative would be this one up here. X, and this would be 1 here and negative square root of 3. That would still be the same, have the same value, plus that's at the minus side, and this would be 5, 6 pi. Okay, so the other would be either minus pi 6 or positive 5, 6 pi plus n pi. The book used this one. You could have used the minus pi 6, either one. Okay, I actually like minus pi 6 better because if we were doing this another way, we would have taken the inverse tangent of that, and then this is even in the inverse tangent. Negative pi 6 would have been. So that's why I went with that one. But the book used this one, which is perfectly fine too. Okay. See how we got those? The general rule is solve for the trig function first, and then try to solve for the variable. Okay. Now, if it's one of our favorites, and this one, anytime you have 1s, 2s, root 3s, root 2s, good chance it's going to be one of those that we know and love so much. Okay. All right. That was example 2. Let's try example 3. They don't have this in the PowerPoint either, so let's do this on the same slide. And this will be solve this one. Cotangent x cosine squared x equal 2 times cotangent x. Now that almost looks like it could be an identity. But when they say solve it, that sort of implies it's not an identity. Okay? Okay. So, it says solve it. What might you try to solve it? And I think that quite possibly, Tyler's idea on the last one probably would come into play here. Why? Okay. Here's the deal, folks. This has 2 trig functions in it. So how can you solve for a trig function when there's 2 of them there? So if you want to try to remedy that situation, maybe then, if you're going to have 2, get them in sines and cosines. That would have been maybe the good answer to that. So what would this be in terms of, well, wait. Hang off that for a moment, okay? Now that I look at this again, let's get everything on one side of the equation and 0 on the other. So let's try that first. What would you do? Subtract 2 cotangent x from both sides. Okay. What does that leave us with? Negative cotangent x times, okay, cosine squared x is equal to 0, right? What's that? Because I subtracted. Oh, wait. That's not added, is it? Woo! Okay. Scratch that. Okay. All right. Minus 2 cotangent x equals 0. You're subtracting it from both sides, so it's this term minus that term. Good catch. Next. Okay, if that were a regular equation, as in ab squared minus 2a is equal to 0, what would you do next? Okay, factor it out. Very good. What can you factor out of this one? A cotangent x. And that leaves you a cosine squared x from that term. What else? Isn't that 2? Okay, good. That's equal to 0. Okay. Now, okay. Now what? Really tight windows we have here. This is a well-constructed building. Huh? Oh, does he? Is he our resident ghost? Okay, I see. Okay. All right. Now that you factored this, what could you do? Equal to 0, something called the zero product principle. What's that? If you have two entities multiplied together equals 0, what does that tell you about? That's what? One or the other, or both, right. So either cotangent x is equal to 0, or cosine squared x minus 2 is equal to 0, right? Okay. Now we get to a question is, where does cotangent x equal 0? It might be helpful now, finally, to use Tyler's suggestion. What is cotangent x? Cosine x over sine x is equal to 0. Now, what would make a fractional form equal to 0? Something over something equals 0. What on this side has to be 0? The numerator. So forget about sine x. You don't want it to be 0 because you can't divide by 0. So this is true only where cosine x equals 0. And where is cosine x equals 0? Yes, at all your half pi's. This will be at x equal pi halves. Now, normally cosine has a period of 2 pi, right? But if you draw this where it's 0, it's 0 at pi halves, then at 3 halves pi, then at 5 halves pi, then at 7 halves pi, then at 9 halves pi. So every pi from there on. So this one, even though the period is 2 pi, these zeros are evenly spaced, so they're every pi apart. We have Orlandria here. So now we have half the class present, which is better than we had last Tuesday, but we're still missing half the people. Not good. So the answer here is they didn't put a restriction on it at all, so we'll say plus n pi. So you understand why it's n pi rather than 2n pi, right? Okay, I bet it. Okay. So that's one part of it. Let's do the other part. Cosine squared x minus 2 is equal to 0. What would we do here? Add 2 to both sides. That sounds like a wiener, okay? That gives us cosine squared x is equal to 2, right? And then what would we do? Take a square root of both sides. That would give you cosine x is equal to plus or minus the square root of 2, right? Now, what angle x would give you a cosine of square root of 2? Really? It's a good guess because the square root of 2's do go with those 45s or pi fourths, but what is square root of 2? Approximately. Do it on your calculator. It could be the cotangent, but this is a cotangent, it's cosine. Okay? 1.414, blah, 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 blah. It's an irrational number, right? And what angle will give you a, when you take the cosine of what angle do you get close to 1.4? Let me ask it another way. Cosine of any angle stays between? Yes, and 1.4 is? Above that, negative 1.4 is below that. Ain't gonna happen. Can't do it. No way. Because cosine is always between plus and minus 1. So this part has no solution. Okay? So your only solutions here are these. Is this. X equal pi halves plus or minus plus n pi. Now, I can almost imagine how they write it. Oh, they actually wrote it right. Okay. Amazing. I have a problem with them, though. Oh, okay. This is the whole function, not just the cotangent part. I thought they were graphing the cotangent. I said they got it wrong, but no, they got it right. So these are all your half pi's. Okay. There is a checkpoint there. It sounded like to me that was enough of a tooth pulling exercise that I think it would be a good idea to work the checkpoint. All right, now we're ready finally for equations of the quadratic type, which some of these have been. Okay, so now we're saying we're going to do those. Many trigonometric equations are of the quadratic type. Ax squared plus bx plus c is equal to 0. Okay? Here are a few of these. 2 sine squared x minus sine x minus 1 is equal to 0. That's just like the quadratic type. Rather than variables, you have trig functions there. Here's one secant x. Secant squared x minus 3 secant x minus 2 is equal to 0. Yeah? Instead of x's, you have secant x. Okay? Here's 2. Okay. This is the same as that. It's just written differently. This is the same as that. It's just written separately. So what do we do? Just like we've been doing. To solve the equations of this site, first factor the quadratic when it is possible. In other words, solve for sine or solve for secant, and then go from there. If you can't factor, you can still use the quadratic formula, only the thing is now your secant x will equal minus b plus or minus the square root of it again. You do it there with secant x rather than x. Here x would be minus b plus or minus the square root of b squared minus 4ac blah blah. Here it would be secant x equal minus b, where that would be negative 3, so it would be a 3 plus or minus 9, and then you go and just plug in the coefficients like you did before, but you're doing it for secant x, not for x. Okay. If you can factor, though, factor. All right, this time they said find all solutions of this quadratic function in sine. This time they give us an interval, 0 to 2 pi. So you won't have plus n pi at the end. You'll have a finite number of solutions. Usually 1, 2, 3, something like that. So where would you begin? All right. Jasmine's here. Okay. So we're up to 6, only missing 4 now, which is better than last time when we only had 4 and we're missing 6, which the others should still come in though. All right, where do we begin on a problem such as this? Where will we begin on a problem such as this? Okay. Let's imagine this problem was 2y squared minus y minus 1 is equal to 0. How would you begin that? Excuse me. How would you begin the problem? Okay. How would you begin the problem? Factor it. Very good. And we factor in terms of sine, not in terms of the variable. So, what's the only possible factorization of 2 sine squared x? 2 sine x times sine x, right? Okay? Where do we look next? Well, actually the sign of the last term. What is it? Negative. What does that tell you about these two signs that go here? They've got to be different. So one's positive, one negative. You have a preference? This is trial and error here. Plus, minus. So we put plus here, minus here. And what's the only factorization of 1? 1 and 1. Okay. We don't know if that's right or not. Let's try it. And we'll do it just like we would if these were polynomials. They're not. They're signs. We FOIL it. 2 sine times sine is 2 sine squared. That checks. Then we do the outer. 2 sine minus 1 would be minus 2 sine x. 1 times sine x would be plus sine x. Add those together, you get minus sine x. Perfect. And then you get minus 1, and that works too. So yes, that was the correct factorization. No wonder he's smiling. Okay, so where do we go from here? Okay, you factored it successfully. I'll take these out because they're not necessary anymore. Okay, you factored it successfully. What do you do now? Say again? Set each of them equal to 0. So either 2 sine x plus 1 is equal to 0, or sine x minus 1 is equal to 0. Okay? Where do you go from there? Excuse me, where do you go from there? Excuse me, where do you go from there? Okay? Say again? Again, you solve for sine x. And how do you do that? Subtract 1 from both sides. And that gives us 2 sine x is equal to negative 1. Divide by 2. And that gives us sine x is equal to negative 1/2. Okay? Let's just go and get the other one done too. What would you do there? Add 1 to both sides, and that gives you sine x equal 1. Okay, let's start with the first one. Sine x is equal to negative 1/2. Okay? First thing I would ask you, where would x have to be, Waldo? Where is sine negative? Say again? Third and fourth only. Because sine is positive first and second. So it's negative in the third and the fourth. So you're going to be somewhere down there. So let me draw a circle. It's going to be a 2 circle, not a unit circle. And I don't draw circles well at all. It's got to be somewhere over in the third or fourth quadrant. I'm going to draw the fourth quadrant first. Sine is what? What is it in terms of x, y, and r? What is sine? Y over r. Okay. So then the y here is minus 1. So the y minus 1 is down here. So it's either here or here. So it's either this angle or that angle, right? Maybe I should have used a different color there. No, cosine is x. Sine is opposite, right? If you draw an angle here, the opposite side is the y, the adjacent side is the x. Okay. Okay. So, those two angles, okay? Now, I know it's been a long time, but what angle has a sine of anywhere close to 1/2?
There's 7 over 6 pi.
Okay?
Or 11 over 6.
All right. It's pi 6 is what I was looking for, and that means pi 6 past the horizontal, which the horizontal would be 6 pi plus this, that would be 7 pi. And over here, you're 1/6 pi short of 2 pi. 2 pi would be 12 pi, so this, sure enough, would be 11/6 pi. Okay. So those are the two angles here. Either x is, and by the way, those are the only two angles between 0 and 2 pi. Okay? We're staying between there, so we don't have to do our plus 2 and pi. You just list those two angles. Either 7/6 pi or 11/6 pi. Okay? How about the other one? Sine x equal 1. Where is sine equal to 1? Where is sine equal? Second? Half pi. At 1/2 pi. Okay, x equal pi halves. At 3/2 pi, it's -1. Okay, but we want it positive. So the only one in our first time around is going to be a pi halves. Because remember, y value is the sine. And go back to a unit circle now, that is one only here. Here at 0 again, -1, and back to 0. So that's the only place on that one cycle around the unit circle that it'll be pi halves. So those are your three solutions. X equals 7/6 pi, 11/6 pi, or pi halves. Only three places. All right. That was example 4. Yeah, example 4. I'm trying to, there it is. X equals 7/6 pi, 11/6 pi, and pi halves. Got it. And they do show you the graph of that on, if you had a graphing calculator, you could have produced that if you wanted to. By the way, that one does have a checkpoint. I would definitely give a shot at the checkpoints. All right, let's see. Okay. Let me clear my ink. Any questions on this before I clear it? Okay. Let's see how they did it. First thing, they wrote it again. Okay. It is a quadratic in sine x. It's already set equal to 0. So you factor it. When you factor it, they get 2 sine x plus 1 times sine x minus 1 equals 0. Set each of those factors equal to 0. 2 sine x plus 1 equals 0. And sine x minus 1 equals 0. On the first one, that will give you sine is equal to -1/2. They subtract the 1 from both sides, divided by 2. The other one gives you sine x equal 1. Where is sine x equal -1/2 between 0 and 2 pi? Well, that's true at 7/6 pi and 11/6 pi. It has to be in the third or fourth quadrant for sine to be negative. And the angle that gives you a sine of 1/2, the reference angle would be pi 6. So pi 6 past the horizontal here, and before you get to the horizontal there. 7/6 pi and 11/6 pi. On the other hand, sine x equal 1 is only between 0 and 2 pi, only going to happen once at pi halves. X equal pi halves. Okay. That was example 4. They're skipping example 5. Okay, so let's do example 5. Any questions? 2 sine squared x plus 3 cosine x minus 3 is equal to 0. Anything a little disconcerting about that picture? happy with it? What's bothersome about it? Anything?
Yes, I need
Oh, you have sine and cosine, so how can you have a quadratic in one function if you got two functions? So that means you must obviously need to eliminate one function in favor of the other, which seems to be the easier to change to the other. And here we would use our identities, wouldn't we? What identity relates sine and cosine? Second? All right, the Pythagorean identity. That would enable us to get the sine squared into cosine squared, and then we'll have an equation only in cosine squared. So that's where we're going to head first. What is the identity that takes you from sine squared to cosine squared? Anyone remember? Second? I think. Say it a little louder. I think you were saying it before. Sine squared x plus cosine squared x is always equal to 1. Always. That's an identity, not a conditional equation. Now, I want to get sine squared in terms of cosine squared. So what would we do? Isolate the sine squared. So what would we do? Subtract cosine squared from both sides. Okay, and that gives me sine squared x, these go out, is equal to 1 minus cosine squared x. Now, you can keep doing that as many times as you want to, but after a while, I think you should say, oh, I know sine squared is 1 minus cosine squared. But do it as many times as it takes, which means do a lot of homework exercises that you're required to do that, and after a while, you'll get to know it. You know, it's like, wait, I don't have to solve that again. I know what that is. All right, so now we got a sine squared x here. Let's plug that in here. 2 times, instead of sine squared x, we'll write 1 minus cosine squared x, right? Plus, that goes in for sine squared, 3 cosine x minus 3 is equal to 0. What next? What next? What next? Say again? I couldn't hear you. Okay, it's already equal to 0. What do we have to do to clean that up some? Clear those parentheses. Distribute. What does that give you? 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. Now what can we do? A little louder? I can't hear. Not yet. Combine like terms. 2 minus 3 is -1. So let's combine those two like terms, and that gives you minus 2 cosine squared x. I had a minus on it, disappeared. Plus 3 cosine x minus 1 equals 0. Now, is there anything you don't particularly like about that expression? What's that? It's cosine. You don't like cosines at all, do you? Okay, that's not what I meant. Okay. I don't like a leading negative. I just don't like it. I wish we could do something about it. Is there anything we could do? How what? Second? You could factor it out or multiply it out. either multiply or divide it away by my minus 1. Because this is an equation, you can do that. Do both sides of the equation, it's legal. So I'm going to make that a plus, and make this one a minus. I just multiplied everything on both sides by minus 1, and 0 times minus 1 is still 0. Okay, I feel better about it now. What can you do now? And this is where what you said before. Let's try factoring. It's a lot easier to factor with a plus in front than it is a minus. So, what's the only factorization of 2 cosine squared? All right. Tamari's here. We're down just to missing 3 now. DeJarian, James, and EJ. Okay. We're on example 5, bottom of page 367 in chapter 5, analytic trigonometry, 5.3, solving trigonometric equations. We got it into a form that looks like it's probably okay to try factoring. Can we factor that? What would be the only factorization of 2 cosine squared? 2 cosine x times cosine x. Okay? Now, where do we look next? Well, the sign of the last term. It's a plus. What does that tell you about these 2 signs? They've got to be the same, and since the middle sign is negative, they've both got to be negative. Very good. And what's the only factorization of 1? 1 times 1. Now, we're not guaranteed this is factored. This may not be factorable, but let's check it and see. Okay, first we'll do the first. 2 cosine x times cosine x, sure enough, is 2 cosine squared x, right? Then we'll do the outer. That would be minus 2 cosine x. Inner is minus cosine x. That adds to minus 3 cosine x. That works. And then minus 1 times minus 1 is plus 1. Sure enough, that works. So our factorization was correct. So let's erase this stuff so we can have room to write. I'll take off the check marks too because they're not essential for the problem, though I don't need that space. What do we do from this point? You've got 2 factors multiplied together give you 0. What does that tell you about those factors? Say again? At least one of them or both of them have to be 0. So we set them each equal to 0. 2 cosine x minus 1 is equal to 0, or cosine x minus 1 is equal to 0. Now this problem, it just says solve it. It doesn't give us any limits on what x need to be. So this one, just expect it, folks. You're going to have probably a 2n pi, or n pi. You're going to have something after your solutions. Next, add 1 to both sides. Is that what you said? That gives you 2 cosine x is equal to 1. And now, divide by 2. Okay? And that gives us cosine x is equal to 1/2. Let's write it over here. Cosine x is equal to 1/2. Now, for what angle x is the cosine 1/2? First, in what 2 quadrants could you be? Where is cosine positive? First, absolutely everything's positive first quadrant. And third. Okay, all students. Fourth quadrant. It is a calculus take, it's take calculus, okay? So, yeah, cosine is positive in the fourth quadrant. So, we're looking in the first or fourth quadrant, and again, I'm going to draw a two circle rather than a unit circle. I don't draw any kind of circle very well. You're in the first or fourth quadrant, and what is cosine, by the way? How is it related in x, y's, and r's? Cosine is a little louder. Yes, it's x over r, right? Your r here is 2, your x is 1. So when x is 1, you're here, your r2 is there. So you're either up here, and in the fourth quadrant, you're down here. Whoa, wrong place. That line is out of place. Okay. Man, this time of day, I don't know what it is about my head starts clogging up. Did it yesterday, and I think the day before too. Okay. So there's where we are. What angle is represented by this? Angle X here. And since the book's been doing it this way, we'll assume the other one's going to be this way. We'll also have an X here. Second, pi thirds, very good. So this is true when X is equal to pi thirds. Okay. And because then you do it once a cycle, plus 2n pi. Because they didn't put any restrictions on us here. And what's the other angle over there? Second? Okay. It's 1/3 pi short of 2 pi. And 2 pi is how many thirds of a pi? Yeah, the answer is 6/3 pi. This x is 6 pi. No, I'm sorry, 5 pi. 5/3 pi. This is 1/3 pi. And this is 5/3 pi. So the other answer would be 5/3 pi plus 2n pi. Okay? That takes care of that one. How about the second equation? The second factor. Add 1 to both sides. And that gives us cosine x equal 1. And where is cosine x equal 1? No, it's -1 there. It's -1 at pi. Because your cosine is your x value. Okay, 2 pi, which is the same as 0. Okay, so it would just be every 2 pi. Because it's 1 once a cycle. So it would be 2n pi. Okay, 2n pi. So those are the ones, either pi thirds plus 2n pi, 5/3 pi plus 2n pi, or 2n pi. Okay? Because it starts at 1 and hits 1 again every cycle. So they have 2n pi, pi thirds plus 2n pi, and 5 pi thirds plus 2n pi. Good for them. Okay? They don't do example 6 either. So let's clear the screen. And do I need to keep that up any longer? Y'all got it? Okay. So let's do example 6. Oh, man. Find all the solutions of this. Cosine x plus 1 is equal to sine x on the interval 0 to 2 pi. So we're going to restrict it to just one spin around the unit circle. Okay? How in the world are we going to solve an equation like that? What's the problem with it? It's an equation with two unknowns in it, two functions in it, cosine and sine. Can't do them with two. So we need to eliminate one. Now that would be, when could you do that with sines and cosines? What enables you to, what kind of identity do you have that relates sine and cosine? Pythagorean identity. And in all the Pythagorean identities, what's characteristic? What about your trig functions? They're squared. Here, neither one of them are squared. So what might be something you would have to do? Square them. Okay, let's do that. Time out, though. Anytime you square both sides of an equation, you may be introducing what they call extraneous roots. This works for variable equations or trig equations. It works for them all. So therefore, we got to check our answers. Anytime you square both sides of the equation, you've got to go back at the end and verify the equations are valid. We should be doing that anyway, just to make sure we got the right answer. But so, as you suggested, let's square both sides of the equation. Okay? What would the first one be? Left-hand side. Cosine squared x. What's next? Plus what? Plus 2 cosine x. I'm sure that's what you were saying, right? Okay. Are you through there? Plus 1. Excellent. Okay. Is equal to sine squared x. All right. Well, you still got sine squares and cosine. You still got sines and cosines within the equation. But what are you able to do now? Say again? Now you can use your trig identity and express sine squared in terms of cosine squared, right? What a trig identity would that be? Okay, and how does that go? What is sine squared? What is sine squared in terms of cosine squared? Say again? I think we're finally getting a little March wind. Right at the end of March, we're finally getting it. What is sine squared in terms of cosine squared? Pythagorean identity. Say again? Sine squared x plus cosine squared x is equal to 1. That's absolutely correct. But we want to isolate the sine square so we can put in that. So what would you do to isolate that? Not like we haven't done it already today. Say again? What? Say again? Okay. You said that was the identity. You're absolutely right. It is. But what we want is what sine squared is, not what sine squared plus cosine squared is. So how do we take that identity and write a new identity, but only in terms, solve for sine squared? How do we do it? Subtract cosine squared, just like we did about 15 minutes ago, right? So that gives us sine squared x is equal to 1 minus cosine squared x. And as I said about 15 minutes ago, or 30 maybe by now, that, after you use these enough, you'll recognize that is, haven't we been there before? Yeah. So now we can write this is equal to 1 minus cosine squared x. Okay? So cosine squared x plus 2 cosine x plus 1 is equal to that. Now what do we do? We do what? How so? What are we trying to get? Hint, it's a quadratic equation. What do we want quadratic equations to look like? Say again? Equal to 0. Excellent. So we need to get everything off of one side except 0 and everything onto the other side. So which way would you suggest we go? I agree with your arm wave there. What did that mean? Do what? Okay, and how do you do that? You don't just pick it up and move it. What do you have to do? Okay, subtract what from both sides? Okay. How about let's do it in a term at a time? Add cosine squared x to both sides and subtract 1 from both sides. All right, what does that give you on the first term? 2 cosine squared x, 1 plus 1 is 2, okay, plus 2 cosine x, that adds a 0, that adds a 0, that adds a 0, so this is equal to 0. Okay? Now, what would you do next? Factor. What would you factor? How about 2? 2 cosine x, and what do you have left? Cosine x plus 1 equals 0. Okay? Now what? Second? Well, you got two entities multiplied together equals 0. What does that tell you? 0 product principle. One or the other has equals to 0, right? So either 2 cosine x equals 0 or cosine x plus 1 equals 0. Let's take the first one. What would you do with that? Not subtract, that's multiplied. Divide by 2. And 0 divided by 2 is 0. Okay. All right, so cosine x is equal to 0. Where is that true? It's where? And let's see, was there any restriction here? Which one are we doing? 6? This is on the interval 0 to 2 pi. Yeah, there it is. So where on that interval 0 to 2 pi is cosine x equal to 0? Would it help to draw a little unit circle? Or not? It's up to you. You said pi or pi halves?
Maybe pi or 2 pi.
Okay. Okay. What if I don't like either one?
Well, then you.
Okay. Where is cosine x equal to 0? Where? Huh? The half pi, of course. So it's either pi halves or there's one more, 0 to 2 pi. 3 halves pi. So this one will reduce, this one produces, I'll put it over here, x equal pi halves or 3 halves pi. That's in this range, okay? So that's what this one does. Okay, how about let's do the second equation. What would you do here? Subtract 1 from both sides, and that gives us cosine x equal -1. Where is cosine x equal -1? Second, at pi, exactly. And that's the only place it is one time around the unit circle. So that's x equal pi. So there are your three values, pi halves, pi, and 3 halves pi. I've got to find the problem. Here it is. Pi halves pi and 3 halves pi. Are we done? Why not? We have to check it because we originally squared both sides of the equation, which means we may have introduced some extraneous roots. So we have to go back to the first equation, which is, I'm going to wipe out some of our little scratch here. Take off, whoa, it didn't take it off. Okay. Take off the squareds. That was our original equation. Now we have to plug these three answers in there to see if they work. What is cosine of pi halves? What is cosine of pi halves? Say again? 0. Plus 1 is? 1. What is sine of pi halves? 1. Pi halves works. Okay? Let's go to 3 halves pi. What is cosine of 3 halves pi? Zero. What, and 0 plus 1 is? 1. What is sine of 3 halves pi? Is 1 equal -1? No. Throw that one out. Okay? Let's go to the third one. Pi. What's cosine of pi? -1 plus 1 is? 0. What is sine of pi? 0. All right. So we got our two solutions. One of them didn't work. It worked in our equations, but those equations we got from squaring both sides. And guess what? We had this, what if you remember, we had 1 equal -1, and you know that's not true, right? But if you square both sides of that, 1 squared is 1, and -1 squared is also 1. So the squared one works, but it didn't before. So you have to throw out 1. And sure enough, we got the two. X equal pi halves and x equal pi. All right. Let's move on to functions involving multiple angles. Okay. The next example involves trigonometric functions of multiple angles of the forms cosine KU and tangent KU. You could have sine of KU. Usually we'll stick to those three. We don't usually mess around with secants and cosecants and usually not even cotangents. To solve these equations, okay, remember when we're solving equations involving sines or cosines or any trig function, you first solve for the trig function, then you solve for the variable. Well, guess what? Now you have something else. So you have to solve for the trig function, then you solve for ku, and then finally you solve for u. So it's a three-step process now. To solve the equations in this form, first solve the equation for the trig function, they leave that one out, then solve for ku, and then finally solve for u by dividing your result by k. So it's just one more little step there, but you have to be careful with it and pay attention. So here's the example. Solve this. 2 cosine 3t minus 1 is equal to 0. How would you begin that problem? What would you do first? What would you do? Okay, yeah. You first solve for cosine, and you do that by adding 1 to both sides. And that gives us 2 cosine 3t, that adds 0, is equal to 1. Now what? Again, solve for your cosine. What would you do? Divide both sides by 2. Okay? Done. That gives you cosine of 3t is equal to 1/2. Feels like we've been here before, doesn't it? Okay? Now, next, we solve for 3t. Not for t, for 3t. Okay? What angle 3t would give you, and they don't give us any limitations on this at all, no. What angle 3t would give you a cosine of pi halves? Okay, we're drawing a circle help. Okay, first, where is cosine positive? Second? First and fourth quadrant. So let's draw us a 2 circle here because our denominator is 2. That's going to represent the radius, right? Because cosine is what? Cosine is what in terms of x, y, and r? X over r. So the r needs to be 2. That's why I did a 2 circle, okay? And the x has to be 1. That puts us in first or fourth quadrant, okay? So either it's this angle here or this angle here. So either that one or that one. My circle is not too good, but what angles would those be then? What would be that angle right there? Pi thirds, okay? So that means that 3t is pi thirds, okay? Plus, because they didn't put any restrictions here, cosine has a period of 2 pi, so it would be 2 n pi. That's what 3t is equal to, okay? Let's go on and do the other one. What's the other angle here? That angle. Five thirds pi, you're absolutely right. 5 pi over 3 is 1/3 pi short of 2 pi. 2 pi would be 6/3 pi. 1 from that would be 5/3 pi. So also 3t is equal to 5/3 pi plus 2 n pi because it can go round and round and round and round and round. Okay? That gives us, we now solve for 3t. Now we solve for t in both cases. And how do we do that? Multiply by 1/3 would be a good way to think of it. Multiply by 1/3, multiply this by 1/3, and multiply this by 1/3. Okay? This will go out, leaving you t, and this will be pi ninths plus 2/3 n pi. That's exactly how you do it. Actually, multiplying by 1/3 probably helps you see it best. So multiply this by 1/3, this by 1/3, and this by 1/3. Okay? That's multiplied. Okay? The 3's go out here, so t is equal to 5 pi over 9. 5 ninths pi plus, and this will be 2/3 n pi. That is your solution. First solve for the trig function. Then solve for the argument of the trig function, which happens to be a multiple angle, and then solve for the variable. 3 steps. Sort of like the Texas 2-step, only different. Okay, never mind. All right, let's see how they did it. Okay? We'll erase all that ink. First thing they did was write the equation again, which was really good. Okay? Next thing they did was add 1 to both sides, and that gives us 2 cosine 3t is equal to 1. What we're doing is solving for the trig function, cosine. And next step to do that is divide by 2, so cosine 3t is equal to 1/2. Okay? Now that they've got that done, what I don't know is why they changed the fonts here. I mean, this trades drive me nuts, but it's not important. And then we have to solve for 3t. What angle 3t has a cosine of pi halves? And you were very correct in saying it was pi thirds, but also in the fourth quadrant, that would be 5 pi thirds. Okay? So then that, but because there's no limit on this, you have to put the plus 2n pi here and the plus 2n pi here, because the period of cosine is 2 pi, and you're adding as many periods as you need to, or subtracting as many periods. But that's what 3t is. Now we solve for t, and we do that by dividing by 3, if you want to do that, or multiplying by 1/3, whichever way you see best. And they say dividing by 3, so that will wipe out the 3 here. Since you're dividing by 3, that puts the 3 in the denominator pi ninths, and that way puts 2n pi over 3. I said 2/3 n pi, or 2/3 pi n, or whatever you want to do. This one does the same thing, divide by 3, that gives you t, divide by 3, that's 5 ninths pi, and divide by 3 here is 2/3 n pi. There's the denominator. Make sense? Is it? How sad. Oh, we got a minute? Okay, we got a minute. All right, that was example 7. That means we didn't get to example 8. That's where we'll pick up next time. Huh? What's that? And it has a checkpoint. Please do the checkpoints. We almost made it through 5.3. Let's see. Homework exercises here. I know that you just hate having a whole week off with no trig to do, so here's some trig to do. Any of the odds 5 through 9. Any of the odds 11 through 23. Any of the odds 25 through 37. And any of the odds 39 to 43. And we'll stop there and pick up and do the rest later. Okay. Y'all have heard the good news, bad news situation, though, haven't you? Yeah, the good news is next week is spring break. But the bad news is we won't meet next week. Sorry about that. So get over it. Hey, good time to get your papers written, isn't it? This is one of my best classes, right? Has 1 paper turned in out of 10 so far. Please get those papers done.